Good morning. We've reached, I think, about 8 people watching. I wasn't quite sure how many we'd get. Certainly our last early morning slot 2 weeks ago proved to be quite early for some of you. It's interesting how quickly we get out of routine. But it's lovely to see the 8 of you that are here. And this is likely to be a slightly shortened lesson. As I described yesterday, this is kind of just finishing off from what we learned yesterday about microphones and loudspeakers. I don't intend to cover anything new. Next week, we'll learn about transformers, and that will take at least those 2 lessons, and possibly going into the week after that, we'll see. But it's lovely to see you all. There's now 9 in the room, and we'll start in the usual way. So, title in book. I've just kept it as microphones and loudspeakers, but I've added a dash and then the words practicing knowledge. So it's microphones and loudspeakers, practicing knowledge, the title of today's lesson. We'll put 3 minutes on the clock, do the usual jobs, please, and then we'll start with the quiz, as we have been doing recently. 3 minutes. We're into our last minute. I didn't make it as clear as I did yesterday, but there's a quiz coming up, so once again, just make sure you've got some scrap paper ready if you prefer to complete it on that. We're doing a quiz in about 30 seconds. Right, thank you very much. And we're up to 10 in the room, so welcome to all 10 of you. We'll start with a quiz, and as is now our sort of routine, I'll do 5 questions on stuff from longer ago and then 5 questions more recent. I'm pausing a minute because I think the cat's about to interrupt me. Oh no, she's stopped. We've not seen Rex in the lessons for a few weeks now, in fact. So, first 5 questions on stuff that you've learned somewhere within the past 2 years. Starting with this, question 1. I'd like to sketch a diagram, and I'd like to sketch the free body force diagram for an apple floating on water. That's a deceptive question because actually you need to understand quite a lot to even understand what the question means, but could you please sketch the free body force diagram for an apple floating on water? Question 1. Question 2, and I hope I've given about the right amount of time there. What are the risks of exposure to X-rays? Question 2, what are the risks of exposure to X-rays? Question 3, sorry I paused longer than I needed to then. I thought the cat was about to distract us again. She walked just undershot. I was about to walk on my computer keyboard, seems not to have done so, we're fine. Question 3, another IV characteristic. You had one of those yesterday. Could you sketch this time the IV characteristic for a fixed resistor? Could you sketch this is question 3, the IV characteristic for a fixed resistor? Question 4 is what is AC or alternating current? What is alternating current is question 4. Right, is indeed string sniping. I've never heard the term, but that's exactly what she's trying to do. She leapt up onto a windowsill, which I've not seen her do for years. She's an old cat. She is clearly showing off to the world. Question 4 was what is AC? Question 5, what are, let's go for two advantages of hydroelectricity. What are 2 advantages of hydroelectricity? Question 5. Right, I'm hoping you've not had to write too much for those. We'll go through them. First, a free body force diagram for an apple floating on water. Well, again, I'll just have to come towards the screen with this one. Sounds more complex than it is, perhaps, but let's start with something roughly apple-shaped. And this is an apple that's floating on water. So let's put that in. None of that is the force bit of this free body force diagram. You can actually be surprisingly precise with what we do here. So there's 2 forces essentially acting on this apple. When you do A-level, you'll actually see it's a slightly more complex picture than that. But I'm labeling from the apple's center of gravity, I'm labeling its weight. That's one of the forces acting. But it was no coincidence that I used the word floating here. The fact it's floating tells us something about the forces. It tells us that the forces are balanced. In other words, there has to be an equal and opposite force acting on that apple, keeping it where it is. Now, I don't mind where you label this force, as long as your second arrow is about the same size as this one and going in the opposite direction. I think the best place to label it is actually from the underside of the apple, because the force I'm about to label is upthrust. And upthrust acts, we could call it the buoyant force as well, but it acts from the surface that's touching the water. So I'm going to label it from here, and I'm going to aim, and this is a sketch, but I was aiming to make sure that the size of this arrow is the same size as this arrow, and I'll label it upthrust. And a free body force diagram like that tells the story. This apple's floating, and it's floating because the forces acting upon it are equal and opposite, so it doesn't go anywhere. That was question 1. Question 2 was what are the risks of exposure to X-rays? Well, I hope your answer was somewhere in this area. If you mentioned that they could cause cancer, I'd accept that answer, or increase the risk of cancer. Perhaps the best answers would explain why as well, and say that it's because they can cause mutations. Maybe the very best answers go right back to the fact that X-rays are ionizing. So a good answer would have all those facets in it. So it would start by saying, because X-rays are ionizing, they can cause cell damage and gene mutation. And because they can cause gene mutation, they can increase the risk of cancer. That would be somewhere around what a good answer would be. Question 3 was an IV characteristic, this time of a fixed resistor. Well, fixed resistors are more or less the only thing that obey Ohm's law. And so perhaps it's a little bit of a misnomer that it is called a law, because it's a law that most components break. But Ohm's law on an IV characteristic graph is direct proportion, straight line passing through 0, 0. That's the IV characteristic for a fixed resistor. Question 4, what is alternating current? Just make sure that your answer has this idea that it's current that flows in one direction then the other. It's current that changes direction. It often changes direction periodically in a sort of a waveform in a regular way, but as long as it's current that changes direction, then you have alternating current. And then question 5, 2 advantages of hydroelectricity. Well, one of the greatest advantages is that in use, it doesn't produce any CO2. You may also want to cite the fact that it's renewable as an advantage. You might have talked about things like the cost to run it is essentially free. You don't have to pay for the water to flow. The disadvantage, and that wasn't the question, but a disadvantage would be its cost to build or damage to wildlife. But in terms of advantages, I think the best ones are, doesn't release CO2 in use, it's renewable, and it is free to operate. Once it's been built, there are no costs associated with running it, really. So that was the first 5 questions. The next 5 are all more recent. And you're getting very used to some of these being repeats, but that's the whole idea. It really firms them up in your mind. So question 1 you have heard before, not for a couple of lessons, I don't think. The question is this: where is the strongest field in an electromagnet created by a coil of wire? And I'm talking about the solenoid there, so I'm going to say that question in a second and different way. Where is the field strongest in a solenoid? Question 2, name a device other than a motor which uses the motor effect. Name a device other than a motor which uses the motor effect. Question 3, the places on a magnet where the magnetic forces are the strongest are called the what? So the places on a magnet where the magnetic field is the strongest are called the what? Question 4 is a question about Fleming's left-hand rule. And I simply want to know what the second finger, and for avoidance of sort of doubt there, I'm not talking about the thumb. So there's thumb, first finger, second finger. And I want to know what the second finger represents. That is for question 4. And then question 5, I'd like you to name 2 things, please, that increase the strength of an electromagnet. 2 things that increase the strength of an electromagnet. Right, I'll go through those 5, and then, well, we won't start with any new learning. We'll just introduce the questions I'd like you to do. So the first question, where is the field strongest in an electromagnet created by a coil of wire? Within the coil is the answer. So when you have a solenoid, there's actually a very strong uniform field running through the middle of the solenoid. So within the coil was the answer. Question 2, name a device other than a motor which uses the motor effect. Well, we saw yesterday, probably the best answer here, loudspeakers. Of course, I'd accept headphones there as well, because they're just small loudspeakers. One we didn't mention, but actually school bells. The bell that rings to begin and end each of our lessons at school is a use of the motor effect. And we'll possibly talk about that in a future lesson in a little bit more detail. Question 3 was, the places on a magnet where the magnetic forces are the strongest are called the, and the answer was poles, the magnetic poles. Question 4, in Fleming's left-hand rule, the second finger gives the direction of the electric current. And question 5, name 2 things that increase the strength of an electromagnet. Well, you could talk about increasing the current running through the wire, running through the coil. You could talk about increasing the number of turns. I might even accept something like adding an iron core, because remember, most electromagnets are wound around an iron core. And so those three things increase the strength of an electromagnet. So that was the 10 questions. Again, for your own sake, you can sort of keep track of marks out of 10 or 2 sets of 5 there. Well done if you did well on them. We're going to start with some questions then. So they're simply the questions that I asked you to print out last time. One starts about waves, and so it'll be interesting to see what you remember about that. When you're doing these questions, by the way, probably always best to have books shut and really just test your own knowledge and see what has stuck. Then there's a question about how loudspeakers work. And just a little sort of note on that. I was not quite satisfied with the notes we took yesterday. I was reading back over them this morning. So I'm going to ask you, when you're answering that 6-mark question, to really try and add detail into what you're doing. Bits of physics you feel I might have left out in the notes we made. And then we'll go through and see how complete an answer you can get with that. And in fact, yes, they were the only 2 questions I gave you. So there's kind of 9 marks there. And so perhaps appropriately, I'll give you maybe 10 minutes, slightly more than a mark a minute. Really try and craft a really good answer, especially to that main question. So I'll give you 10 minutes, then we'll go through them. And for today, that will essentially be our lesson. 10 minutes, as always, ask any questions you wish as we're doing this. I will otherwise just stand here nice and quietly, but just ask any questions you need to ask. 10 minutes. You've had just over half your time. There's, as you can see, if you can just about make out the timer on me, there's about 4 minutes left. I think this will be enough time for everyone, but again, I'll ask the question in a few minutes' time if you're going to need longer. For now, just keep going and we'll go through it in 4 minutes' time. Two minutes ago, by all means, just call out through the comments if you need a bit longer, but in 2 minutes, we'll go through it. So there we have it, 10 minutes. I hope that was enough. And I'll just be adjusting the camera now as we go through it. So bear with me 1 minute. Nearly there, just going to zoom in a little bit as well and make sure it's nicely focused. That didn't work. Well, pressing autofocus has made it, if anything, less focused. Just give me a minute. Right. Technical problem to solve. I just need to make sure it focuses. I apologize. That's better. Just needed something clear to focus on, like a pen. Right. So this first question, less about magnetism, more about waves, but I think you'll appreciate that in the things we've been learning recently, there is a huge amount of crossover. Understanding the two things together allows you to understand complex things like microphones and loudspeakers. So question 1 started with waves may be either longitudinal or transverse. Describe the difference between a longitudinal and transverse wave. And it's worth 2 marks. And it's one of those questions for which there is a stock response. So, questions asking about describing differences, I think often have the word whereas somewhere in the middle of them. But we've got to describe the main difference. And so your description of longitudinal, and these are going to be in note form, but your description of longitudinal waves should have made reference to the fact that the vibration is parallel. The vibration is parallel to the direction of the wave's travel. The vibration that creates the wave is parallel to the direction of the wave travel. I'm underlining that word because I think it has to be in your answer. Actually, that's not quite true. If you said in the same direction as, that will be fine. But the best way to put that is parallel. That's where I personally would drop in a whereas. And we just need to give the converse statement for transverse waves. So in transverse waves, the vibration is perpendicular. Sorry, it's a bit scruffy there, but again, it's the pen just to make sure that you can see it. And again, I'm going to underline the word perpendicular. I think that should be in a good answer. But again, perhaps that's not strictly necessary. If you said that the vibration creating the wave is at 90 degrees to wave travel or at right angles to, that would be fine as well. Now, in a strange way, I think part B of this was the hardest one because it's only worth 1 mark, but it's unusually open for a question that we get in physics. It says, describe one piece of evidence that shows when a sound wave travels through the air. So I've written over the question. It is the wave and not the air itself that travels. So describe one piece of evidence that shows when a sound wave travels through the air, it is the wave itself, the wave and not the air itself that travels. A strange old question. This may be one where you want to check through the comments if yours is right. But the answer that occurs to me is something along the lines of this. Is that when an object makes a sound, wave, and this is what occurs to me, when an object makes a sound wave, a vacuum isn't created around it. A vacuum is not created around it. That for me is a piece of evidence. If, like the question suggests, if when a sound's created, the particles travel with the sound, then you might expect that when an object makes a sound, it creates an area without particles around it. Or you might expect that when you're in a room and someone's speaking into an orchestra live, you might expect to feel movement of air coming off the orchestra, if that assertion were true. The fact that you can't feel any of those things is evidence, at least, that the particles themselves don't travel. They vibrate, they transfer their energy, but they don't travel from A to B, even though the sound wave does travel from A to B. So I hope you have a sense of whether your answer fits that. But that one there was certainly the answer that occurs to me. Right, the 6th marker was about loudspeakers. So the figure below shows the parts of a moving coil loudspeaker. A coil of wire is positioned in the gap between the north and south poles of the cylindrical magnet. And yes, our diagram didn't have a magnet like this. I wanted to keep it simple, but that's more typical of the sort of magnet you get. You get something that's magnetized in such a way it has a north pole around the edge, and then sticking up through the middle of it is a south pole, or vice versa. The question goes like this. Explain how the loudspeaker converts current into an electrical... Explain how the loudspeaker converts current in an electrical circuit into a sound wave. Essentially, we're being asked to describe how the loudspeaker works. And we've got to take it from the current to the production of a sound wave. We're very much practicing what we did yesterday. So here's some of the things I think a good answer would have. I think we've got to reference that the current is alternating. This would not work. Remember, this would not work if it was just a standard amount of direct current. If it were a fixed amount of direct current, yes, this would feel a force, but it would feel a force once, and the cone will get pushed forward or backwards and just stay where it was. It wouldn't vibrate to make a sound. So it's really important your answer has that the current is alternating. And so the coil, and I don't remember putting this in our notes yesterday, experiences a force. It was implied. It was implied, but we didn't necessarily put it. So I think a good answer mentions that the coil experiences a force. And then perhaps the next point links those two things. So as current alternates, the direction of force alternates. And I think we've gone a long way to describing that now this cone vibrates, and that's always a good answer to a good word to have in your answer. So I think there's a little bit more detail in that than we put in our notes, and you may wish to reflect on that and add that to your notes. We've still not got to the final part of the answer, so we'll carry on. So once we've described that this coil is vibrating, we can say this makes the cone vibrate. Because remember, the coil is attached to the cone. And I think you can really show off in an answer like this. We can bring our knowledge of waves into this. And we can say that the cone creates, and I'm going to say compressions and rarefactions. And I'm going to put in adjacent air particles. In other words, the particles just next to the cone are compressed together, and so the ones just beyond them are spread out. They become a rarefaction. And so what we're describing there is a sound wave propagating. So I'll say sound wave propagates. And again, I think that's just another really sort of impressive sounding word to put in there. And it makes a lot of sense. It's not just about showing off. It's very clear and very well chosen words for expressing physics. So there may be things that you've put that are different to that are still equally right. And hopefully you have a sense of judgment on this now that lets you know whether you've got it right or not. In terms of assigning a mark to it, I know these things matter less in these lessons. But anything that has most of these, you can give a 5 or 6 to. If you feel there's any sort of glaring omission there, then you can drop it down to 3 or 4. But knowing you as I do, I expect most of you have done a very good job on that. So yeah, we have this idea that if you have an alternating current, that means that it alternates. In other words, the coil vibrates. And if the coil vibrates, the cone vibrates. And so that cone then creates areas of compression and rarefaction in the air particles that are near it. In other words, a sound wave propagates. And so we've answered the question. We've gone from explaining how a current in an electrical circuit is converted into a sound wave. Well, that's the lesson. I'm just going to make some final remarks and a suggestion for something you can do in the coming week. So let me just turn the camera around so I can say my thank yous and my goodbyes. Well, I'll start with the recommendation. I bang on about Carl Sagan a lot, and he did a series called Cosmos, and the original Cosmos was in about 1979, 1980, all on YouTube, by the way. This isn't the recommendation, this is a side recommendation, but the original Cosmos is a brilliant thing, an inspiring thing. I do recommend it. But what I'm actually recommending is that it was remade. Now, Carl Sagan has long since died. He died in 1996. But an astronomer called Neil deGrasse Tyson, helped by Carl Sagan's widow, who's still alive and well and making television still, they made a remake of the original Cosmos in 2014. Now, it covered some different things compared to the original, but one episode, and I seem to remember it was episode 9 or 10, was called The Electric Boy. I've kept that on screen long enough, hopefully, that you have the details. I'll just say a little bit about it. So The Electric Boy is the story, really, of Michael Faraday. And it's a really well-crafted episode. He is absolutely one of my favourite scientists. He came from nothing, and that's unusual in the history of science. You can imagine that for hundreds of years before we had universal education, most of the people who could do science were fairly rich, because they were the only ones who'd been taught to read and write for very long. And legend kind of has it that he was forced out of school because his teacher teased him for his speech impediment that he had. So history doesn't record that he went to school for very long at all. When he was very young, he became a bookbinder's apprentice. And so he had access to books all the time, and he read voraciously. And he also went to the very first public lectures that the Royal Institution of London put on, the Royal Society, sorry, put on in London. And so he was exposed to science, and he just got the bug for it. And then the episode goes on to show his discoveries. So the things we've learned about, the motor effect, the generator effect, he sort of, not quite single-handedly, but more or less gave us the science that allowed us to make motors and the science to make electricity generators. But then perhaps most movingly of all, it shows, and this is very unusual for a scientist, that I think when he was in his 60s, he started to get dementia. Now, what's unusual is that most scientists do their best work in their 20s. And yet, Michael Faraday, despite the fact he had dementia, unlocked one final secret of the universe. He discovered the nature of light waves, that light waves are electromagnetic waves. In other words, they have an electrical component and a magnetic component. And that bit of understanding basically unlocks our modern communication. So the fact you can see this now, the fact that we can watch live broadcasts from across the world, all hang on understanding the nature of electromagnetic waves. So he gave us that too. And he seems to be singled out by the fact that he was at a loose end. You may, through certain streaming services, have access to it for free. You may be able to buy the DVD or the Blu-ray, order it on Amazon and have it delivered to you. But if you have the kind of spare money to do that, and the spare time and the spare inclination, I really recommend the Cosmos series, and especially that episode, The Electric Boy. Right, in terms of things for next week, I'm planning to do the usual, Thursday and Friday. The Friday one, of course, will be a bit later in the day. And we'll learn about transformers. So my homework between now and then is to try and build a transformer from stuff I have at home. Never tried that before, really intrigued to see if I can do. But I've been thinking about it, and I think I've probably got everything I need to build a transformer to show you. So that's for next week. And again, just watch your emails, because I'll be sending out, there will be some things to print out and maybe some diagrams to print out that we can label together. I'll let you know later in the week, probably on Wednesday. So until then, stay safe as always. I hope you're still okay. I hope you're all still in good spirits. Thank you as ever for tuning in. It is quite sort of moving to me that you still want to put that time in. And I will see you in just under a week's time. I'll see you on Thursday. So bye for now, and thank you.